Okay, so I hope that this will work now, with the PowerPoint being able to flip through the slides. So I'm just going to share my screen here. Okay, and then I'm going to do the slideshow from the beginning. So hello, welcome to the EECE 1202 final exam review. I'm going to be covering mostly some theory, just very small calculations because this exam is mostly about memorizing the theory behind microcontrollers slash microprocessors, ADCs, and analog to digital communication. So we're going to start off first with the embedded systems and then jump into microprocessors, microcontrollers. So what is an embedded system? Well, basically, an embedded system is a programmable computer embedded inside of a device to provide added functionality or features without making the device much larger than it needs to be. And some characteristics of embedded systems include being specifically applied. So it does have certain specific applications specialized for one application or one class of applications. The next characteristic would be that it's very lightweight, usually lightweight and low volume, because they're meant to be embedded inside a host system, as we described before. They're also deadline constrained, so the system has to be able to reach its goal within a certain time frame and achieve successful results by that time. It's also ideally power efficient. It must be able to conserve power so that the system itself can last longer. It can run for a much longer period of time. We would ideally want these embedded systems to run, to not be able to just instantly crash, right? So we would make that happen by conserving power to maximize life. And it, of course, has to be manufacturable, so small and inexpensive to create. What's not an embedded system? So they're not general purpose computers the way like a laptop or a desktop are. Some examples of things that have embedded systems are smartphones, GPS systems, wearable medical devices, most computing systems. And then we kind of dive into why we need these embedded systems. So we have four different kinds of needs. So communication slash networking, signal processing, control systems, and general computing. General computing is like your general needs such as video games, wearable computers, ATMs, etc. Communication and networking refers to things like telephone systems and internet, where you're going to do a lot of switching and information transmission. Signal processing is computation involving large data sets. So applications would be radar, sonar, and video compression. Control systems, you'd want to make feedback controls of real-time systems. So this would be especially important in flight control and vehicle engines. And we have kind of a picture here from the lecture slides. Again, I really, really encourage you to go through all the lecture slides and familiarize yourselves with the material covered in class. So we have this basic structure, and I'd want you to familiarize yourself with the structure of an embedded system. Then we jump into the two types of computing systems, microprocessors and microcontrollers, or the two types of ways they can be classified. So they're both digital electronic components with lots and lots of resistors, capacitors, transistors, etc., integrated on an IC that is supposed to be small, remember that form factor, and power efficient. So you'd want to know the differences between a microprocessor and a microcontroller, just the main differences. One of them is where memory and I/O are located. So for a microprocessor, they would have to be on external circuitry connected to the chip, whereas on a microcontroller, the memory and I/O capabilities are embedded inside the chip. Microprocessors are generally used in heavy-duty systems like personal computers, and microcontrollers are more specifically applied, such as MP3 players. You know that they play music, and that's kind of their only function. And you'd also want to know the advantages and disadvantages of both microprocessors and microcontrollers. An advantage of a microcontroller over a microprocessor would be the fact that it's more compact and it's rather cheap. Disadvantages of microcontrollers, so where microprocessors become kind of more suitable, would be in places where you would need more customization because your hardware circuitry can't be changed. So a microprocessor would be great for if you are working on a project where you need to customize more, or if you need to multitask. And I have a few different examples of each. Well, one example for a microprocessor and two for a microcontroller. So Raspberry Pi, your little computer, as many know it as, is a microprocessor, and a microcontroller would be Arduino. So you've worked with Arduinos in the labs in 1202. And the TI Launchpad, which you would probably be able to work on in Fundamentals 1 lab. So next you'd want to know kind of the differences between each device. So Arduino versus Raspberry Pi versus TI Launchpad. You want to know some common uses of each. For example, the Raspberry Pi is most commonly used for simple projects as it is your little tiny computer. Your Arduino is very versatile and easy to use for simple projects like the Raspberry Pi, but it does have your open source hardware and integrated development environment, which is very, very, very nice. And your TI Launchpad, which is basically a product line of over 30 microcontrollers. It's each Launchpad, so each TI Launchpad is a microcontroller unit, and specifically the MSP 432 P401R is using the widely used ARM 32-bit Cortex. So that's a fun thing to note about the TI Launchpad. You'd want to know kind of the different processor capabilities of each device. So your clock speed, memory, communication protocols that are supported, and also the operating system. So Raspberry Pi can use its own operating system called Raspbian, but it can also run Linux and I think maybe some other operating systems. But yeah, that's kind of what you would want to know about each device as far as this exam, just knowing a brief overview of the processing capabilities, common uses, operating system, number of pins, communication protocols, that kind of thing. And that's where I'd want you to go back into that microcontroller, microprocessor, PowerPoint, and kind of really take notes over that. Also, taking notes over important definitions. So we've talked about embedded system, microprocessor, microcontroller. You'd want to study your baud rate, UART, universal asynchronous receiver transmitter, which you kind of explored in a previous lab where you played with the receiver and transmitter of Arduinos. Your 32-bit ARM Cortex-M4, which we talked about previously when talking about the TI Launchpad, and some basic Arduino commands, which you've already worked with. You've already coded some things during the labs, but just knowing for sure what each one does. So serial.begin, analog read, digital write, serial.println, and delay. Those are some commands that you really need to be familiar with. So those are some important definitions that you'll want to know. Next, we get into the analog to digital conversion. So you had a lab before where you were kind of looking at the analog to digital conversion using an Arduino, which has a 10-bit ADC. And you were able to convert, you were able to get an output ranging from 0 and 1023. Those were your quantized steps. But for ADC, you have 3 different stages. You have your sampling stage, your quantization stage, and your encoding stage. So for a sample, you would do it by the process of sampling, which is where you take the analog signal, which is a continuous time, continuous valued signal, into a discrete time, discrete valued signal. And you do that by taking samples, which are values or a set of values at the analog signal, and you would figure out what values to take by figuring out how often you sample at, so your sampling rate. And we know that a higher sampling rate leads to a better digital signal that can more highly, that is more accurate to the original analog signal, that can represent it in the best way, in a better way. So when we sample, because we want a good sampling rate that will accurately represent the original signal, we want to prevent aliasing. So over there, the image, I took the image from the slides also. It's an example of aliasing where whenever the signal is sampled at those dots, those black dots, you are either going to represent the blue signal or the red signal as each of those signals, as both of those signals pass through the dots that you've created on the page. So that's aliasing, where you have the sampling representing more than one signal. It's not necessarily accurate to one signal. So how we can prevent aliasing and make our representation accurate is to take the Nyquist criterion and multiply it by 110%. For the Nyquist, we take the highest frequency of the signal and multiply by 2. But for the Nyquist criterion, we'd want to prevent aliasing by sampling at a frequency that is greater than 2 times the maximum frequency of the signal. So a good way to do that is to take that and multiply it by 110%. So let's say you have your highest frequency is going to be 50 kilohertz, and you're going to multiply it by 2. So yes, that would be your Nyquist, which is 2 times your maximum signal frequency of the signal, which is 50 kilohertz. So it'd be 2 times 50,000 times 1.10, which is the 110%. And so that would be your new sampling frequency that you would sample your analog signal at to prevent aliasing. Then we move into the quantization part. where you're kind of figuring out the resolution, the number of bits to represent a sampled analog signal. So here you would figure out the step size of your analog to digital conversion. So let's say you're using 8 bits to represent each signal sample. So you would call that an 8-bit ADC. And you will get from this 8-bit ADC 2 to the power of 8 levels. So 2 to the power of 8 is 256. So you would be able to represent 256 different discrete values for the signal. Quantization is the process of mapping input-out values from a large set to output values in a smaller set. So your analog signal has a bunch of different values, a bunch of different outputs, but you want to be able to convert it to a digital signal, kind of reduce the number of different values that represent the signal. The different levels, as we talked about before, is 2 to the n, where n equals the number of bits, 2 to the n levels, so 2 to the n different discrete values that your conversion will have. And then once we get into, because we're getting into the quantization part, we want to also look at the quantization size, so your step size between each output level. So let's say you have a 3-bit ADC. So the number of levels that you will have will be 2 to the power of n, where n equals 3. So 2 to the power of 3 is 8. That's the number of levels that you have, number of different discrete values that your conversion will take. But for the analog voltage, your original range is from 0 to 12 volts. And we're kind of keeping it that way, but we're having the quantization determine the size between each step, each level. So your quantization size, aka your step size, is going to be your maximum end of your voltage range minus the minimum end. So for a 0 to 12 volt range, you would do 12 minus 0 divided by the total levels, which is 8 levels for this ADC, which is equal to 1.5 volts. So in between each level, you're going to have a 1.5 volt difference. You will then be able to, in each level, make its own state. So each stair step, if you will have its own output state. So once you're at 0 volts, the next step up is 1.5 volts, the next step up is 3, and so on and so forth. Oops. Next, we get into encoding, where we have these output states from all the stair steps, right? But we want to kind of represent that using digital values. So we're going to give it an output binary equivalent. So we said that output state 0 is at level 0. The next stair step up is going to be 1, next stair step up is 2, etc., etc. And then for each of those changes, so 0 is a state, right? Then you would, for the encoding, you could do 0, 0, 0 for 3-bit resolution, 0, 0, 0 to represent 0. Then for 1, you do 0, 0, 1. Then for 2, you do 0, 1, 0, just those numbers in binary using a 3-bit representation. So that's the encoding part. Then we evaluate the conversion by looking at the signal to quantization noise ratio, or SQNR, which is the ratio of the signal power, represented as PX, to the noise power, which is represented by PQ. Over here, I forgot to mention that the part after the word or, so the SQNR equals 10 log SQNR. I forgot to denote that this one would be your calculation in dB. So your SQNR in decibels is going to be 10 log your SQNR, so the PX or PQ, which is equal to approximately 1.76 plus 6.02 B, where B is equal to the number of bits used to quantize the signal. So let's say your quantizer is 16 bits. So then your SQNR in decibels is going to be 1.76 plus 6.02 times 16. Next, we want to go into analog communication systems. So this is one thing that's very, very important to memorize, is the block diagram of a communication system. So you want to know what goes before and after a certain stage. So you have first the input transducer, then the transmitter, which might attach a carrier, and then the channel, then the receiver, then the output transducer. And you want to also take a note of the little pointers going to each arrow. So you see at the beginning, there's the input message, then in between the input transducer and the transmitter, there's a message signal. So the message signal goes from the input transducer to the transmitter, and the transmitter takes then the transmitted signal goes from the transmitter to the channel, and etc. You want to know what's in between each block. So the input transducer, an example could be like a microphone or a camera. It converts the input message, as you see in this block diagram here, to a message signal, which is then going to go into the transmitter. And you can see that clearly in this block diagram. The input message could be anything like speech, video, any other type of data. Then when the transmitter has the message signal, it'll encode the message and may attach a carrier if you're trying to do some wireless communication. So then that transmitted signal will go into the channel, which is a carrier for the signal. So it could be something like a wire. Then the wire takes that signal and it will go to the received signal is going to the receiver. So it converts the signal to an output signal. Then the output signal is going to go into the output transducer. The output transducer could be something like a video monitor or a speaker. So a speaker would be used in the case where your input transducer is like a microphone. So you're talking into the microphone, and then the output is going through the speaker, the output transducer. The output transducer converts your receive signal into an output message. So you would be getting like the speech from the microphone or the singing or anything like that. You want to know some examples of communication systems, of course. You want to know about your radar, just kind of what it is. Electromagnetic waves are radiated and detected after reflecting off of objects, and it's based on the Doppler shift. So that's your radar. Then this goes into sonar, which is similar but uses acoustic waves. And you've probably like already seen some applications with this, just kind of underwater navigation, anything like that you've been exposed to. Then we want to move into the spectral analysis. So you're going to be given the message signal and the carrier signal in a problem, and you're going to figure out the different frequencies whenever you're trying to get the transmitted or the received signal. So given the message and the carrier signals, you're going to figure out the blue here, transmitted signal, and the purple, received signal. You're going to see that for the transmitted, you have 4 different values. For the received, you have 6 different values. And you just use your information given about the message signal and the carrier signal, and you're going to make those computations. It's very easy, just addition and subtraction of different signals. So for the received signal, this gives you a bit more information. These are also all from the slides. So we're using a low pass filter to eliminate the high frequencies. So usually the carrier signal is much higher. Carrier signal frequency is much higher than the message signal frequency. So those frequencies for the carrier signal gets filtered out while the message signal gets passed. That's the end of the slideshow, but I just wanted to let you know also to look at your digital communication systems, as we did go through analog communication systems. Your block diagram is going to be the same as it is like basic elements of a communication system, but just knowing like the differences between analog signals and digital signals. For example, analog signals, infinite possible values, right? As we discussed before, we're talking about ADC. And we kind of go over the advantages of digital communication over analog communication, as in digital communication has a bit more, can kind of be able to survive against noise and interference. And that's just one example of an advantage. Another example would be that digital communication is cheaper, and you kind of want to know some basic elements of a digital communication system. So we have your basic elements of a communication system block diagram that you really want to know and memorize, but specifically a digital communication system has these parts, but the slides kind of go more into detail about the components that you're using, and so I definitely recommend looking at that diagram. And yeah, digital communication systems, I would have you go through each of the slides and look over the different terms, the theory, just as we did with the analog communication systems PowerPoint. But yeah, since this exam is a lot about the theory, I would definitely encourage you to brush up on your theory, really be familiar with different concepts applied here. Otherwise, you can review things from past exams, as I think maybe there'll be some, like a few problems sprinkled in, just maybe a few about material from past exams. But like I said, it is mostly the theory, as I recommend definitely focusing on going through these slides and learning the theory more. But if you do have any questions about anything from the past exams, like the stuff from the past exams was definitely a lot more things that you had to solve out, and it was definitely a lot of math. So if you do have questions about those, feel free to direct message me, Teams, Discord, anything like that. But otherwise, yeah, that's the end of my exam review for CEEE 1202. And let me know if you have any questions again. So thanks for listening, and I'll see you later.